Okay, this week we're talking about the physical properties of soil. So you probably remember this from the first day. This is an idealized soil here. We've got about 45% will be mineral components. That's sand, silt, and clay. And that's primarily what we're talking about today, although we will delve into organic material a little bit. And ideally you have 50% pore space, and hopefully each is about half water, half air. Okay, this is a really great visual on the differences in the different soil particles. Sand is the largest particle that can be seen with the naked eye. Silt needs to be under a microscope, and clay needs a specialized microscope. It's really tiny. So sand, if you have a sandy soil, it doesn't stay together, so it doesn't aggregate, which is really important to hold moisture in the soil. Much of the sand that we have is quartz-based. It's the most resistant to the weathering, and it's very slow to break down, and it really doesn't contribute anything to plant nutrition. Silt is too small to be seen with the naked eye. It's very fine. You're going to see it in riverbeds. It feels like flour to the touch. And then clay is the smallest mineral particles, of course. It's the active portion of the soil. Chemical reactions occur at their surface, and adsorption and release of plant nutrients happen here. And clay particles have about 1,000 times as much external surface area as the particles in an equal weight of sand. And you may have thought I misspoke, but adsorption and absorption are two different things. Adsorption just means that it's going to attach itself to the surface of, in this case, soil. Absorption is when things are taken up, like with roots. So soil texture is how coarse or fine a soil is. It's the percentage of sand, silt, or clay in the soil, and this is something we're going to do in our lab on the 22nd. Loamy soil is what you want. That's equal influence from sand, silt, and clay, but a very small amount of clay has the greatest influence on soil texture. If you look at this triangle, if you go up to 20% clay, that'll be on the left-hand side here, you start to see clay in the name of the soil. Soil texture is the relative proportion of sand, silt, and clay. And of course there's various sizes to sand, so there's some very coarse sand or very fine sand, but again, silt and clay are much smaller. So soil texture is one of the most important properties of a soil. It greatly affects land use and management. It affects the amount of water and nutrients that a soil can hold and supply to plants. And it can influence structure and movement of air and water through the soil. And this is crucial. So the parent material, of course, weathered plant material and soil forming process determine the horizon's texture. Here's some two different types of soils with different plant material. Texture is relatively permanent physical property under natural conditions. It's not practical to change soil texture. As I mentioned on the first day, that if you add sand to clay to try to help with porosity, you're actually going to clog up those pores, and it's going to become concrete. Soccer fields, in many cases, they'll be adding sand to the soil to increase the depth of the roots of grass, but that needs to be sandy soil to begin with. Otherwise, they're going to have some big problems. So you can have your soil texture tested in a lab. We're going to actually do this in class. Not necessarily how they do it in a lab, but we are going to do two different types of tests to determine soil texture on your soil. In the field, you can do it by feel, and that's one of the things we're going to do, and it's kind of a process of elimination. And if you've done any dichotomous keys for determining plant identification, you'll be familiar with this type of situation. So basically, soil textural classes are based on the relative proportions of the soil separate, sand, silt, and clay. There are 12 different soil textural classes, and we use the texture triangle to determine the textural class, and we'll do this in class, in lab. Okay, here's your triangle again. So the percentage units, 0 to 100% of sand, silt, and clay are listed along the sides of the triangle. Also notice that the relative proportion of sand, silt, and clay adds up to 100%. So when you're talking about soil texture, only sand, silt, and clay are used to determine it. It's only the mineral fraction of the soil. Organic matter is not considered when determining texture or textural class. And if you're really going to do a precise analysis of soil texture, you need to remove the organic matter, and this is usually burned off. Okay, so here's our optimal soil. On the left here, we've got a nice amount of organic matter. We've got our perfect amount of water and air. We've got our mineral matter. Clay soil, you'll see that this is getting to be more water and less air. And then with sandy soil, you'll see there'll be more air and less water. Soil structure is another way we look at soils. This is the arrangement of aggregates or beds in a soil. It creates different sized pores. It can retain adequate water. It can allow for drainage. And the forces that cause soil particles to bond to each other are biological, chemical, and physical, and we'll talk about each one of those. So soil microorganisms excrete substances, and those are cementing agents that help bind soil particles together. Hyphae, which are fungi, extend to the soil, and they'll help extend soil particles together. You'll see the picture on the right is actually hyphae in soil. Roots also excrete sugars, and that helps bind minerals. Okay, so soil organic matter can improve aggregation. It can improve water holding capacity and surface area. It can also increase nutrient availability. This is included in our nitrogen and phosphorus cycling solubility. It increases cation exchange capacity, which is what we discussed on the first day. We will continue to discuss that throughout the quarter. And then it buffers against pH changes. And of course, biologically, it increases microbial diversity. It helps with nitrogen fixation, helps with phosphorus availability, which is through mycorrhiza, and increases pathogen suppression. So always a good thing in your soil. And here's just a sample of what it might look like. You've got some bacterial colonies here. You've got fungal hyphae binding these soil particles together. There's some organic debris in there, which would be humus. That's the stable portion of organic matter. Here's our mineral soil particles and some of the exudates that are gluing the soil particles together. Okay, so as I mentioned, microbial and fungal byproducts glue the particles together. You've got on the left-hand side, we've got our dispersed state. Here is that glue, and then you've got an aggregated state. So here's another look at it. We've got a soil particle, we've got a soil aggregate, and then finally you've got aggregates that become soil structure. Now soil structure has there's different types of soil structure. Granular soil structure you're going to see in a dark surface soil. Blocky you're going to see in a clay-enriched subsoil. And you can see that that's not really a great way for water to penetrate. Prismatic, that would happen in subsoil of grasslands. Columnar, these are vertical columns of soil. This happens in more of a salty grassland situation. Platy, that's an alluviated subsoil, usually found in compacted soil, and you can see water's not going to really be moving through that. So, soil structure can be destroyed by compaction or excessive tillage. Tillage of wet soils can definitely damage structure. And of course, loss of organic matter can weaken soil structure. So here's a picture of soil on the left that had no tilling for 10 years. You can see it's got nice aggregation. If you look on the right, you'll see soil that's been tilled continuously. There's very little pore space and no aggregation. Okay, so in ideal soil, as I've already mentioned, 50% solid, 25% air, 25% water. So the beige color is the soil solid, the blue is the water, and then the white is air. And so you can see we've got plenty of space for water and air on the left-hand side. But when you get into compacted soil, very little air is available, and water just kind of stays there, if you can get it into the soil. So compaction impedes root growth. It limits the amount of soil explored by roots. It can decrease the plant's ability to take up nutrients and water. And then in dry years, it can lead to stunted, drought-stressed plants due to decreased root growth. And of course, the way things have been going around here, this is our summers anymore. So it's really important that you try to help either avoid compaction or help try to alleviate it. So soil compaction reduces pore space. It increases bulk density, which we'll do in a lab in a couple of weeks. It'll cause root growth inhibition. There's going to be a low water holding capacity because the water is not actually going to be able to get into the soil. Reduced water infiltration and percolation. Reduced aeration and anaerobic conditions, which of course is not good for your roots. And increased erosion. It's almost like when the water hits the topsoil, it just rolls right off. Porosity, we'll be talking about in our bulk density lab. This is the percentage of open spaces or pores. And a lot of it has to do with surface area. So even though clay doesn't have very big pores, it's got high porosity because there's so much surface area. And things like gravel, when it's well sorted, can have high porosity, but when gravel, sand, and clay are poorly sorted, it can be low porosity. So large pores are good for aeration. Smaller pores are good for holding water, and so this is a really nice aggregate or crumb of soil. It's got both small pores, large pores, and intermediate pores. And so when you're talking about water movement in soil, and we'll talk about this more down the road, but gravitational pull has a lot to do with how quickly water will move through the soil, and that's going to be much greater in sandy soil than it is in clayey soil. Capillary action is when water actually moves against gravity and moves back up. And you can see after 24 hours, the green ring there, that's how 36 inches in clayey soil and 40 minutes for sandy soil. So it's really, it can totally affect how quickly water moves through.